All right, you're hanging with Hussick. This one's about predicting precipitates from dilutions and salt mixtures using KSP and solubility values. Okay, so let's have a look at dilutions, generally speaking, and dig into some solutions and apply some things we know about KSP and solubility to these systems. So, to begin with, let's just get back to basics on a solution and make sure we're starting at a consistent spot here. So, if I tell you there's a solution here in the container here, and it's 100 milliliters of 0.1 molar aluminum nitrate. Well, remember that I'm giving you the volume here in milliliters. That would be volume. Capital M is always going to be concentration. And so you should be comfortable with extracting what's the ion concentration of each respective ion in that solution. And there's your two ions. You've got the aluminum ion and you've got the nitrate ion. So how do you figure out those concentrations? Well, remember when you dissolve, or whether you dissolved it or not, when it's present in solution, the aluminum nitrate salt, remember it's going to produce one aluminum ion for every unit of salt, and it's going to produce 3 nitrate ions, isn't it? So we would expect the concentration of nitrate to be 3 times as high as the concentration of aluminum, and then if this is X, we know this is going to be X, and this is going to be 3X. So in this case, we actually knew what our concentration was. They gave it to us at the start. It was 0.10 molar, which means this is 0.10 molar, which means this is 0.30 molar. Okay, so then if we were going to go back up here, we could easily determine what the concentration of each of those ions is. That's an important first step to realize when we're working with these solutions. Okay, so building on that knowledge of determining ion concentrations in solution, we can realize that when we mix solutions together, we're basically diluting solutions in a way because there's a new total volume, okay? And so we have to think back to how we deal with diluting any solution and how the concentration changes, as well as now considering what we know about the different ions and salts and the way they can combine to turn into things that are insoluble. So one step at a time. Let's say, for instance, we are mixing the following solutions, okay? And solution A, if you will, is 100 milliliters of 0.1 molar calcium bromide. And solution B is 200 milliliters of 0.2 molar sodium ethanoate, okay? That's that sneaky little ethanoate ion, CH3COO-, typically written like that, but you need to recognize it is an ion. Okay, and the question is, what's the concentration of each ion in the solution? Okay, so where we would start with this is we would look at each individual salt that was already dissolved, because that's where the moles of each ion is coming from. Remember, ultimately, if we need to do concentration, we know the concentration is moles over volume, okay? And so we'll have to look at each salt and figure out what's the moles, how many moles of each ion, and figure out how many moles is there of each particular ion, and then we're going to have to divide that by the total volume, the new total volume of the solution, which is going to be, let me just switch colors. What's the new total volume going to be? We had 100 and 200, so it's going to be 300 milliliters now. Start filling in some characteristics of our new solution. Okay, and then we can find the number of moles for each of these salts, for each ion, using the characteristics of the initial salt. Okay, so let's go with the calcium bromide. What's the concentration of the diluted new calcium bromide in solution? Well, we know concentration is going to be moles over volume. Okay, we figured out that that new total volume is 300. We'll write that in. But how many moles of calcium bromide are there? Well, we also know that moles is going to be concentration times volume of the initial solution. So let's put that in. So it's concentration times volume of the initial. Maybe I should call it A. Concentration of A times volume of A. okay, over V total, which is going to be 300. So the initial concentration was 0.1, we were told. The initial volume was also 0.1. We had an extra 0 on there. This would be liters. This would be capital M. Okay. Over 300 milliliters, which of course we're going to write in liters, 0.3. Okay. So process that, and you get 0.033 repeating, basically. Okay. What does that mean then? The fact that that initial salt, the fact that that salt finally, we're looking at the final condition because it's V total, has a concentration of 0.033 moles per liter. What's that mean about the concentration of Ca2 plus? Well, you should realize, once again, if I can parse this out for you, that when this dissociates, it produces 1 calcium 2 plus, and it produces 2 Br minuses, right? 2 bromides. So for the calcium 2 plus concentration, it's going to be the same as the salt concentration, 0.033 molar. Again, with 2 sig figs, that's accurate as we can be. And then for the other one, it's going to be that times 2, isn't it, for the bromide? So the bromide ion concentration is going to be, the multiplier of 2 comes into play, so it's 0.066 moles per liter, okay? You do the same with the other salts, okay? So we know that for the other salts, which was sodium ethanoate, okay, we're going to say, what's the concentration of the sodium ethanoate in there? And again, we'll do the same thing. Number of moles of it over the total volume. Moles is going to be concentration of B times volume of B. Again, this is because this is where all the moles actually come from, right? From its initial solution. Okay, then of course we're diluting it, so that's why we're using V total. So the initial volume was 200 and the initial concentration was 0.2. 200 is 0.2 liters. All right. Divided by 300 milliliters. Bop, bop, bop. You get 0.13 moles per liter is the new concentration of that salt after dilution. Then you have a little examination of what would that salt do in solution. Well, it's going to produce each of its ions at a 1-to-1 ratio in solution, isn't it? Because it's going to make just a single Na plus and a single ethanoate ion. Okay, so basically the concentration of each of those salts is going to be the same. Each of those ions is going to be the same as the concentration of the salt. Okay, so the Na plus concentration is equal to the ethanoate ion concentration, and that's equal to 0.13 molars. Molar. That's generally what you would say. Okay, so that's how you'd solve one like this. We're mixing them together. Really, the thing to respect is that all the moles come from the initial solutions, and there's a new total volume to find your new concentrations. By the way, I should say we had to respect the fact in this question that if we examined all the ions that were there, Ca2 plus, sodium ion, calcium ion, sodium ion, bromide ion, and ethanoate ion, that no combination, especially after we do the next type of question, no combination of these ions is going to form an insoluble salt. So we didn't have to worry about there being any solid precipitate. Okay, the next question we're going to try and consider as well, or I'll try and get your brains in the mode of analyzing these to try and see, is there going to be a precipitate happening or not? Do we predict a solid to come out of it? Okay, so take a question like this. let's look at predicting a precipitate quantitatively. So as soon as we say quantitatively in this subject, we know we're probably going to have to start examining things like KSP values, okay? And so you need a list at your disposal for these questions of KSP values for different salts that are at the core of the discussion here, okay? So the question is this: predict whether or not a solid precipitate will form if the following two solutions are mixed. Okay, so we've got basically solution A, 100 milliliters of 0.035 sodium chloride. And I would encourage you to do this kind of thing. Label what the values are you're given. And then we have solution B. We have 150 milliliters of 6.2 times 10 to the minus 4 silver nitrate. Okay. So we're going to mix these two things together. What do we know right away? Well, we know if we mix them together, what's the total volume? Have a look at the total volume. It would be 100 plus 150, so 250 mLs. Okay. We also can then analyze, well, what ions are in solution. And the other thing you would need for this, besides having your KSP values on hand, is you would need a list or a reference chart of what ion combinations you expect to make insoluble precipitates, okay? So you take out your chart of possible ion combinations, and you'll probably see that when sodium and nitrate are together, they do not make an insoluble salt, okay? So we had sodium and chloride, that's totally soluble. We had silver and nitrate, that's totally soluble, obviously. They came as aqueous solutions. Then we have sodium and nitrate, that's totally soluble, so it's aqueous. But if you look at the combination of the other possibility, silver and chloride, silver chloride is an insoluble precipitate, okay? So what we're interested in here is seeing, is there enough of the silver ion and enough of the chloride ion in solution to precipitate silver chloride? Because of course, if there's not enough of it, the salt won't be saturated in that solution and it won't precipitate as a solid, okay? So basically we're gonna have to dig up those KSP values and run a test on that, all right? So I'm going to document what we just discussed here. Okay, so as I've highlighted down here in green, how are we going to do this little test? Well, we have to look at the KSP for silver chloride. So you look up the KSP value, and you find out that the KSP for silver chloride is 1.8 times 10 to the minus 10. Then you're going to run a test. You're going to run essentially what is a Q test or a trial KSP, okay? And if that value for the trial KSP is at or higher than the value of KSP, actual KSP, we know the ions will precipitate. If it's lower, then we know that the ions are not in high enough concentration to precipitate the salt. Okay, so the QSP for silver chloride is going to work exact same way that the KSP expression will, right? It's the concentration of silver times the concentration of the chloride ion, okay? And we just have to figure out what are those concentrations. So to find out the concentration of the silver ion, I'm just going to work aside over here, okay? Let's just work over here at the side. Concentration of the silver ion, we know is going to be the moles of silver ion that was in there over the total volume. Okay, you have to make sure you go check. Let's see. The moles of the silver ion are going to be concentration times volume. So 150 mils times 6.2 times 10 to the minus 4. So 150 mils times 6.2 times 10 to the minus 4 moles per liter. Okay, that, of course I converted the volume to liters. And we said the new total volume is 250 liters, okay? So you do that processing and you get that it's going to be 3.72 times 10 to the minus 4 moles per liter for that ion. Then you're gonna put that into the QSP, but we also have to do chloride, so let's do chloride. Same thing, it's gonna be the moles of chloride ion over the V total. All the chloride ion comes from the original solution that had chlorine in it, which is 100 milliliters of 0.35 NaCl. So I forgot it already. 100 milliliters, 0.35. Concentration times volume. Volume is 100 milliliters. Concentration 0.035. Yes. V total 250 milliliters in the new solution. Okay, and then you crunch those numbers. Beep beep beep, and what do you get for this one? 1.4 times 10 to the minus 2 moles per liter. Okay, so you're going to take these two values that we just determined, and you're going to plug those into the QSP expression. So the Q expression will be 3.72 times 10 to the minus 4 multiplied by 1.4 times 10 to the minus 2. Put that into your calculator, and you're going to get 5.2 times 10 to the minus 6. Okay, so now interpreting that, so we get 5.2 times 10 to the minus 6. How does that compare to the QSP value? So here's KSP value. Here's KSP, here is Q. Well, you can see that the Q is greater than the KSP. So if the Q is greater, that means our ion concentrations are higher, which means it will precipitate a salt. So therefore, the silver chloride solid will precipitate. It will precipitate. Hopefully that makes sense. I'll just sort of zoom the whole thing out so you can see the whole thing at once. Oh, I realized maybe looking back at this whole thing, I skipped one tiny step, or I glanced over one tiny step, which is that realizing the initial salts that you had in the solution up here were like 1-to-1 salts, okay? So that when you have X amount of NaCl, okay, you also have X amount of sodium, X amount of chloride. Same with the silver nitrate. If you have X amount of silver nitrate, then you have X amount of silver and X amount of nitrate, because they're all 1-to-1. So where did that manifest? Well, it meant that down here when we were calculating the ion concentration, we just used those numbers straight up for moles, right? We didn't multiply by 2 or multiply by 3. So you do have to watch those salts a little bit that are added. You may have to use a multiplier like 2 or 3 depending on the nature of that salt. Okay, anyways, I hope this was all helpful and understandable. I'll make a further video for ones that can have added layers of difficulty.